Hi, Calvin. This first problem is a Michaelis-Menten kinetics problem. So I'm going to copy this data and I'm going to paste it into Microsoft Excel. I already did it, but I want to show you how to do that. So I'm going to do it again. May have already become familiar with Microsoft Excel, but in case you haven't, I'm changing this data here to be 1 over S, and that's in units of 1 over millimolar. And to do that, I type the equal sign to say that I'm going to do a formula. And then I click on the data that I want to use. Oh, I'm sorry. Equal sign 1 over. And then click on the data that I want to use. Press enter. Then I highlight that same cell and look for the solid. And turns into a scheme. And I drag that data down and release. Same thing here. Equals 1 over that data. And then skinny plus sign, drag, release. Whoops, division by 0. We don't have data there. And equals 1 over, then a skinny plus sign, drag, and release. This data here, this is with no inhibitor. This data here, this is with inhibitor. Now I'm going to graph this. Okay, why am I doing 1 over? Why am I so interested in 1 over? I'm interested in 1 over because of the because this is a Lineweaver-Burke plot set of data. So this is the Michaelis-Menten equation that you saw in your lecture, and for most enzyme kinetics problems. But if you graph this, you don't get a line. And in biophysical chemistry, we love to use lines. We use lines over and over again for all kinds of different equations. And the reason why we do that is because it is easy to get a best fit line out of some software. And when you have the best fit line, or the linear regression line, you get a slope and a y-intercept. So if we take the reciprocal of both sides of this equation, and then split this so that it's in two separate terms, this term and this term, we have the form y equals mx plus b, where this will be the slope, this will be the x, and this will be the y. So this is why we want to take the reciprocal. So I took the reciprocal of the substrate concentration, which in this case was arachidonic acid. And so this would be the x values. To the substrate of the rates. With no inhibitor, that would be the y values. And then the reciprocal of the rates with inhibitor, that would be the y values for another line on the same plot. Let me show you what I mean. I'm going to highlight these guys and press the control key and keep it down and highlight, oops, wrong one. Highlight these guys. Oops, sorry. Start over. Highlight these guys. Press the control key, keep it down, and then highlight these guys. Right. Whoops. Okay. Okay, that's good. So this is the X I've highlighted, and this is the Y that I've highlighted. I'm going to insert a scatter chart. That nice X and Y, and of course I'm going to click on one of these data points, and then right-click on that, and then add trend line. And I'm going to get the linear trend line, and I'm going to display the equation, display the R squared. So this equation is y equals mx plus b, where the y is 1 over the rate with no inhibitor, and the b, the y-intercept, is 1 over the maximum rate of the enzyme at any substrate concentration. So I have to do this for another set of data, so I'm going to find some white space at the top of this graph and right-click and choose Select Data. And while I'm here, I'm going to edit this first series of data, and I'm going to give it a name and call it No Inhibitor. Right? And then, actually, in order to show you what I'm doing, I'm going to move this over. Okay, let's do that again. So right-click on some white space, select Data, and I'm going to add some data. I'm going to add 10 milligrams per milliliter inhibitor, right? And click on the X selector. Oh, that's not the X, sorry. The X is the same. It's this X. That's the X. Then click on the Y selector. These are the Ys. Okay, and then we have a nice set of points here. Click on OK, and then I click on one of these points, and then right-click and add trend line, and get the equation and the R-squared. These R-squareds are very high. That's probably not realistic. So your professor made up this data somehow, but that's good for pedagogical purposes. I'll probably be stealing this homework assignment for use in a class if I should happen to teach such a class in the future. Now, this is called the Lineweaver-Burke plot, and the slope is kind of interesting, but what's really interesting is the y-intercept and the x-intercept. So I need to stretch this line so that it can show me the x-intercept. So I'm going to do that. I'm going to forecast the line backwards, some number of, so since these x-axis numbers are less than 2, I'm going to put 2 here as my backwards forecast. Press enter, and there it is, backwards forecast. Click on this orange dotted line, not the data, but the line itself. And also backwards forecast, maybe 2, see what happens. All right, so now I have some nice x-intercepts there, and I've got some nice equations to work with. Right now, I need to know which line is which, so I'm going to add a chart element, add a legend here. I like to have the excuse me. I like to have the legend on top. All right, so no inhibitor is the blue, and yes inhibitor is the orange. All right, so let's check this out. What have we got in the way of actual work here? What we have here is a question. What kind of inhibitor is this? All right, so this is obviously a competitive inhibitor. And here's why. The y-intercept is 1 over Vmax, so the Vmax is obviously the same, whether you have inhibitor or you have no inhibitor. Now, if the Vmax is the same, then what is the inhibitor doing? Well, the inhibitor is slowing down everything else. So this is the Km. Now, if you solve this equation for x and you set y equal to 0, that'll be the x-intercept. If you solve this equation for the x, which is 1 over s, if you solve this for 1 over s and set this equal to 0. Now, I know 1 over v will never be 0 mathematically, but the biochemists just ignore that and just say, hey, what if this is 0? If this is 0, then 1 over x is going to end up being negative 1 over km. The algebra is not that hard. You can just do that with a marker on your bathroom mirror and when you have some spare time. Now, since this is negative 1 over km, right, let's just find those things here. So Vmax with inhibitor, Vmax, no inhibitor. Let's find also the Km with inhibitor, Km, no inhibitor. Right, so the Vmax with inhibitor is going to be 1 divided by the y-intercept, which is 0.0194. Right? And same y-intercept over here. Usually, like in a real experiment, it isn't exactly the same, but if it is close enough, then you call it a competitive inhibitor. So competitive inhibitor is the only kind of inhibitor that gives you no change in Vmax. You'll see why in a moment. I'll draw a picture for you. The Km, oh, you know what? I'm gonna have to solve this equation. I'm gonna have to solve this equation for x by setting y to 0. Right? So x equals negative 0.0194 divided by 0.0202. That's with inhibitor. And with no inhibitor, x equals negative 0.01 plus negative 0.0194 divided by 0.011. Okay, so the Km is going to be equal to the to negative 1 over this. Right? Nice. So let's try down. Okay. So we could see that from no inhibitor here, the Km increased by kind of a lot. It's almost double. It did not change. Right? So Km max change with. Now here's why. Let's say this is the enzyme, and this is the substrate. Right? And the substrate does something after it gets worked on by the enzyme. Well, what if you take a drug and it is an inhibitor, and the drug works by looking just like the substrate, except it just takes up space on the active side of the enzyme, and it does not actually do what the substrate does, and so the shape is a bit different, like this. So this part fits in just like the substrate fits into the active side of the enzyme, but the rest of the molecule is is, uh, is not of the correct shape to do the actual biochemical reaction that was supposed to happen. So this is just like a time waster. It's kind of like romance. Like if you're like a girl who needs to get married because of parental pressure, you do not waste your time with players because they're not going to marry you, right? So this is like the player, like that, right? A bunch of players out here are competing for time right here in this enzyme active site. So that is how competitive inhibition works. Let me show you why the Vmax does not change. So if you have a club full of players, and if you have a club full of players, you are going to have a problem finding a true mate. But if you are at a club full of potential true mates, it doesn't matter if there are players. The likelihood that you're going to hook up with a player is very low because there's just these true potential mates are crowding out the players. And this is why Vmax is not changed for a competitive inhibition. See, the player doesn't stick to the enzyme permanently or anything. The player doesn't stick to the enzyme any more stickly than the true mates, than the true substrate sticks to the enzyme. The play is just a casual time waster. So if you just have enough potential true mates, enough substrate concentration, you're going to end up with the same Vmax. So Vmax is the maximum rate of reaction catalyzed by this enzyme given any substrate concentration. Meaning you just flood the enzyme with substrate and you're going to get Vmax. Okay, theoretically you're going to get Vmax. I mean, you will never actually see Vmax, but Vmax is a theoretical limit, upper limit of the enzyme rate. So suppose you had a million true substrates and one player, then yeah, you're still going to see that you're going to still have the same theoretical Vmax. So there's going to be no change to Vmax. Now, this is the only method of inhibition where there is all the other inhibition types uh, will cause a change to the Vmax. So this is the only type of inhibition that will give you the same y-intercept for the inhibited line and the non-inhibited line. Let's look at this Km. So Km increases. That means what that looks like. So um, if you have a club with players and true mates, true potential mates, um, the fact that the player is here makes it seem to the human observer like the 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 enzyme is not sticky enough to the true to the true substrate because the true substrate can be displaced, replaced, or just blocked by the player here, by the inhibitor. So the effect that we observe is that the Km increases, meaning the stickiness decreases. So it seems like the enzyme has this hard time sticking to the true mates because there's too many players. So that increase in Km is what it indicates that there is a failure of the enzyme to stick to the true substrate. Well, I mean, the enzyme is having no problem sticking to the true substrate, but it just seems when you do the experiment, it seems like the enzyme is having problems sticking to the true substrate because of the presence of these players of these inhibitor molecules. Of course, there is no real problem with the stickiness, but it's just these guys are blocking, and so they seem like it seems like there's a problem with stickiness, but there is no problem with stickiness. Stickiness of the enzyme and substrate is not affected here in reality, but it seems to be affected when we do the experiment. We are humans, so we cannot see the enzyme sticking to the substrate. We cannot see this; it's too small. But when we do the experiment, the Km increases. We interpret that as a failure to stick. All right, so let's go back to the question here and actually answer it. So this is a competitive inhibition. Now, your professor wants to see a printout of this plot, so you have to um, do several things when you print out the plot. Of course, even if the professor doesn't specify, every instructor wants to see a good title, and a good title has to be 1 over rate versus 1 over substrate. Without ibuprofen. So some title that describes what's going on here, and then every teacher wants to see you have a, a x-axis with the proper label, 1 over substrate. I guess you should probably say arachidonic acid instead of substrate here, but you also have to say the units. Then every teacher wants, whether they admit it or not, they all want to see a 1 over rate in units in minutes per millimolar. So it's millimolar per minute is the rate, but we did 1 over, so the units are also reciprocal, minutes over millimolar instead. So every teacher wants to see these types of titles. Now, if you want to make it bigger, you can right-click on a white space on top of the chart and then move chart to its own sheet. There, it's nice and big. All right, so every teacher also wants to see this. Actually, every teacher wants to see. Every teacher does want to see the legend, but they don't want to see this part. So I'm going to see if I can remove that. Okay, well, I don't know how to remove that, but I suggest you try to remove that. I don't know how to. Well, maybe it's not so important. But anyways, every teacher wants to see the title and the y-axis labeled with units and the x-axis labeled with units and some kind of legend. Your teacher is also going to want to see this equation, so you make sure to display the equation. Okay, so graphically determine Km Vmax. Okay, so we just did that. So the Vmax is oh yeah, this was my practice session. Let's just delete that. This was the Vmax. This was the Km. Now what's this Ki? So Ki is in part of the factor by which the Km changed. So so this with inhibitor, this is what your textbook calls the Km apparent. Km apparent equals Km apparent equals the original Km times 1 plus 1 over Ki. Right? So let's solve for 1 plus 1 over the Ki. Right? So that means the Km apparent was this. Right? So that was the Km apparent, and it equals Km, which is this number, times 1 plus 1 over Ki. So if I do this, this number, double click on this number divided by Km, so Km apparent divided by the Km will be equal to, so this equals, sorry, keep on putting a space there when I should. This equals 1 plus 1 over the Ki. Okay? I'm just using Excel as a chalkboard here since I don't, I lost the pen that I use to write stuff on the screen. Isn't that annoying? Sorry. So now I'm going to solve this for Ki. So this is going to be this number minus 1 equals 1 over Ki. So now I'm going to solve this for Ki by taking the reciprocal. So 1 over this number equals Ki. So that's the Ki. The Ki is 1.35. Now what are the units of Ki? Well, let's see. The units of the x-axis is 1 over millimolar. That means the units of the x-intercept is 1 over millimolar. But we just, to find the Km, we took the reciprocal of the, in fact, we took the negative reciprocal of the x-intercept. So these are not, the units here are no longer 1 over millimolar. They are actually millimolar. Right? So that means the Ki has to be also, actually the Ki, what are the units of the Ki? This is going to be something times, this is pretty crazy. So the Ki also, what? The Ki should be 1 over millimolar. Ki should be 1 over, okay, I do not know the units of the Ki. It seems from the formula that the Ki should be units of 1 over millimolar, so that you could get, no, the Ki should be unitless, because we're adding it to 1 here, and 1 is unitless, and we have to end up with millimolar for Km apparent. So Km is already millimolar, so millimolar times 1 over, times millimolar would be millimolar squared. So I think Ki formally in the math should be unitless, but in reality, I think biochemists assign units of concentration to Ki. I don't know why they do that. They always do these annoying things with math. You know that 1 over V equaling 0? That never equals 0. Okay, so I think most people consider Ki as having units of concentration. And this is, hang on, millimolar with inhibitor with Ki. Oh yes, yes. So yeah, I think this Ki is usually considered as units of concentration. I'm not sure about that, but I suggest you check me on that in your textbook. So I've got the Ki at 1.7 here. Huh. See these guys? They have this one significant figure here. How is that okay? Then the Ki would be 2. But I don't think you're supposed to respect significant figures here. So I think you have to say Ki is at least 1.7, maybe even 1.74. I don't know. Oh, no, not 1.7, 1.3. 1.3. All right. Now, is ibuprofen a okay? So, is ibuprofen a strong or weak inhibitor of this enzyme? So, I have not seen those words "strong" and "weak" used for inhibitors before, but I found some stuff on Google that indicates that strong inhibitors have a Ki of something like nanomolar or some picomolar, whereas weak inhibitors have some large Ki, such as millimolar or perhaps even micromolar. So I found that by googling strong weak inhibition Ki. So this Ki, now since the units that we are using here is millimolar, so we've got 1 over millimolar, millimolar per minute. So the Ki is seems to be millimolar. 1 millimolar Ki 1 millimolar Ki would seem to indicate very weak inhibition, because Ki is supposed to be picomolar or nanomolar, and here's why. There's some people online who are saying that Ki, well, I'm not sure of that, so I'm not going to mention that to you at this point until I'm sure of that. But Ki is supposed to be nanomolar or picomolar, and the reason is with a higher Ki in millimolar or even micromolar for some substances, uh, you have to take so much of the drug in order to get inhibition to happen that that drug ends up doing other stuff, like the side effects become apparent. So the lower the Ki, the better. So the lower the Ki, so if this number Ki, if Ki is very, very small, that means this fraction 1 over Ki is very large. That means 1 plus 1 over Ki is large. That means the Km apparent is very different from the Km. But if Ki is large, I mean, if Ki is if Ki is large, then 1 over Ki is small. 1 plus 1 over Ki is almost just 1, and 1 times Km is just 1, so your drug didn't do anything at all. So you want a very small Ki. Now this Ki is not very small. It's like hardly more than 1. Like to one significant figure, it is 1. So this is not a good Ki. This is not a good a really strong inhibitor. Ready? So this is weak. This is weak inhibitor, and that's the explanation. So it's so this is almost 1, and 1 over 1 is 1. 1 plus 1 is actually 2. Yes, but 1 over 1 is 1. What if this were 1 over 10? This is 1 over 10. That would be 1.1. What if this is 1 over 0.1? And that would be 10. That would be 11. So maybe it's not very weak. Maybe it's just weak. Because at least it makes, at least it doubles the Km to make Km apparent 2. Well, almost 2. So I would still say that this is weak. So that's it for problem number 1. Have I told you everything that important with this graph? I think I have. Okay. Thank you, Calvin.